remind you that I promised that we will discuss this question. For what integers n, we can find integers x and y, such that n is a sum of two squares, x squared plus y squared. And the first step is to factor the right hand side. X squared plus y squared is, well, just formally, it is such a product where square root of minus 1 is, well, sum. We pretend that it exists. And we'll try to do all the algebraic manipulations as if, well, it is an actual square root of minus 1, actual number. So, first kind of observation. You remember that when we discussed Bell's equation, it was useful to take one solution, another solution, and multiply them together. Let's try to do the same thing here. So if n is x plus, so x squared plus y squared, and n prime is x prime squared plus y prime squared, let's try to multiply these things. So let me rewrite n as x plus square root of minus 1 times y times the same thing as minus sign, same with n prime. So x prime minus square root of minus 1 n prime. And let me multiply n by n prime. So what do we get? N times n prime is the product of this thing and that thing. X plus square root of minus 1, y, and the same thing as x prime and y prime, times the same thing with minus signs. Well, once again, it doesn't seem that this is of the form that we want. Something plus square root of minus 1 times something else, and the same thing with minus sign. But we can combine terms here, like this. Let me combine this with this, and this with that. And open brackets. What do we get? We get that n times n prime is the following sum. X prime minus y. Sorry. Let me go here. So, what do we get here? I open the brackets here. X times x prime plus square root of minus 1 times y x prime plus square root of minus 1 times x times y prime plus square root of minus 1 times square root of minus 1 times y prime. N times the same thing with square root of minus 1 replaced by the same thing with minus sign. So now, here I see the product, square root of minus 1 times square root of minus 1. Well, product of two square roots of the same thing is the thing under square root. So we can write it like this: x prime minus y prime plus square root of minus 1 times y prime plus x prime times same thing with minus sign. Now this does look like, well, exactly is of the same form. It is like this. It is x prime minus y prime squared minus y prime plus x y prime squared, and actually plus. So it's minus square root of minus 1 squared. So if this number is a sum of two squares and this number is a sum of two squares, here we got the formula. The product is also a sum of two squares. And this formula, well, it's obvious once you write it down. Once you have the formula, it's obvious. You open the brackets and you see that indeed n is this thing, and then prime is that thing, then the product is equal to this thing. But before it's written down, it's not that obvious to find it. And to find it, well, we use the trick. You factor this thing, you combine terms, and, well, it worked. And it worked basically in the same way as it worked with the equation that we started with previously, actually, the square root of 2. Just the same idea. Instead of square root of 2, we have square root of minus 1. Is it any different? Well, really not that different. We're only doing some algebra, simple algebra. Okay, so to formalize these kind of arguments, so let's first write down what we prove. So if A, n, and prime are sums of squares, sums of two squares, then n times n prime is the sum of two squares. And the formula is like this. So we have these equalities, then you know that n times n prime is, well, this thing. X prime minus y prime squared plus x prime plus minus prime squared. So once again, once it's written down, it's obvious. Before it's written down and you try to remember it or discover it, well, I would just try to do this thing, exactly this thing. I can't really remember this formula otherwise. Okay, so now to formalize what we are doing, we can introduce complex numbers. Once again, hope that most of you have seen them in other contexts, so it will be kind of brief. But we introduce the following things. So definitions. We introduce a symbol, first of all, for square root of minus 1, we call it I. Just a symbol instead of square root of minus 1, we every time we write I squared is minus 1. That's the basic rule that it satisfies. We call the set of all numbers of the form A plus square root of minus 1b. So A plus IB. If A and B real numbers, we call them complex numbers. And there are some beautiful things about them. For example, we can do arithmetics with complex numbers. We can open the brackets. So we kind of did it already. If you want to say multiply two complex numbers, we just open the brackets. If you have x plus iy, we multiply by x prime plus iy prime, we get x prime plus y by prime times I squared, so minus y by prime plus I times y prime plus x prime. So that's about multiplication. There is a final procedure called conjugation. We replace square root of minus 1 by minus square root of minus 1. And once again, we've seen this procedure several times. I mean, even in the first problem that we solved today, we've seen a final procedure. Take the equation and replace everywhere square root of 2 by minus square root of 2. And somehow it preserved all the algebraic equalities. Some complex numbers, there is a corresponding operation. It's called conjugation. If we have a complex number which is x plus iy, then its conjugate is called, well, it's the same thing, but with square root of minus 1 replaced by minus square root of minus 1. And this conjugation preserves all the arithmetic operations. For example, if you have two complex numbers and you add them up and you conjugate, it's the same as conjugating each one of them and taking the sum. Basically, you write the equality that z1 plus z2 is equal to z1 plus z2, and you replace everywhere square root of minus 1 by minus square root of minus 1. And you get this equality. Same about the product. Conjugate product is product of conjugates. So, one important thing is like this. If z is any number, x plus i1, and you multiply z by its conjugate, you get the following thing. It's x plus i1 times x minus i1. If you open the brackets, it's x squared plus I times minus I times y squared, so it's plus y squared, plus I times yx minus I times yx, so it's plus 0. So it's a real positive number. It's positive and real. And well, for us it will be important because it is sum of two squares, so we'll give it a name. We'll call it norm. Norm. Is z is a conjugate, or in other words, it's z of x squared plus y squared. No, the norm is like this. So there is always, you might have seen some other definition, it's absolute value of z, and it's the square root of the norm. Sometimes it's useful, for us this one will be more useful because, well, so this is square root of x squared plus y squared. This number has geometric meaning, it's kind of the length of the vector or something like this. This number, well, it's convenient for us because if x and y are integers, then this number is also integer. The absolute value isn't. So we'll mostly be using this norm. So, what else? We have norm, division of complex numbers. You can obviously take a complex number and divide it by a real number. So if you have, if alpha is real, you can take x plus iy divided by alpha, and you get such a complex number. Just obvious. But if you want to divide by a complex number, well, there is a trick. If you have z and you want to divide it by w, here's the trick. You take both numerator and denominator and multiply it by the conjugate of w. So a priori it's just not that obvious that this number is a complex number. It's not written as something plus I and something else. But in this way, well, it's z times w conjugate divided by normal w. Normal w is a real number, and this is a complex number. So you know how to multiply complex numbers. So if you wish, let's compute the answer, if we take x plus iy divided by x prime plus I y prime, we get x plus iy x prime minus I y prime divided by x prime squared plus y prime squared. And the answer is the complex number is coordinate s, which is x prime minus y prime divided by, plus y prime divided by x prime squared plus y prime squared plus I times y x prime minus x y prime divided by x prime squared plus y prime squared. So you can multiply the complex numbers, you can divide the complex numbers, you can do everything in complex numbers, all the arithmetics. You can take powers of complex numbers by just multiplying enough times. So, once again, I really hope that you've seen all these definitions before, or all of them except the norm, something like this. What we'll be interested here in this course is definitely something with integers. Integers are the most interesting for us. It's not the reals, it's not the complex numbers themselves. Integers are what interest us, so we introduce the definition Gaussian integers. The notation is like this. It's the usual integers and brackets where brackets are. So it's read integers with I adjoined to them. It's just the following thing. It's complex numbers with integer coordinates. It's x plus iy with x and y integers. So it's the complex element of usual integers. It's all the complex numbers. Well, g 5 plus 3i, 7i, 2, or negative 2. All of them belong to Gaussian integers. So it's just such things. Well, maybe since we are talking about definitions, let me already introduce the Gaussian rationals. Order of definition, Gaussian rationals. I'm just going to introduce a symbol. It's rationals. Once again, we join square root of -1, and it's complex numbers with rational coordinates. And so, in these terms, our question about how to write a number as sum of two squares is like this. Can you write a number as a normal Gaussian integer? So, our question about n being equal to x squared plus y squared. Now can we reformulate it like this? It's both integers are norms of Gaussian integers. And in this notation, what we proved is, we proved that if n is a norm and n prime is a norm, so if n and n prime are sums of squares, then the product is sum of squares. Well, that's obvious in this notation. So if n is the norm of z and n prime is the norm of z prime, then n times n prime is also a norm of what?
Product of that.
Yes, it's n norm of z times z prime. Indeed, what is it? but we know that conjugation of a product is the same as product of conjugates. Conjugate with product is product of conjugates. Now we can regroup it like this, z conjugate, z prime conjugate. And this is the norm of z times the norm of z prime. So the norm of the product is product of the norms, and hence what we proved about sums of squares in this language is, well, at least sounds shorter. Norm of the product is product of the norms, so if two numbers are norms, then their product is obviously also a norm. Well, it's not that huge advantage for now, but let's develop a little bit of the arithmetics of complex numbers, and we'll see much larger advantages. So maybe any questions about just definitions? For now, we didn't do any mathematics, any actual mathematics. We just introduced some notations basically. What is I? How to multiply the complex numbers? What is the norm? Why is the norm multiplicative? So maybe any questions about this? Is there somebody here for whom this review of complex numbers was too fast? So we'd like to try to repeat all the arithmetics that we did with usual integers, but now in Gaussian integers. Where do we start in usual, well, where did we start in the first lecture? We started with the following fact. Every integer can be written as product of distinct primes, essentially in a unique way, and then we started using this to solve, to find all the Pythagorean triples or something like this. Let's see what can we do in Gaussian integers. Say I want factorization in Gaussian integers. Let me take a Gaussian integer and try to write it as a product. It's a natural thing. Let me just try. So let me start with, say, this thing, 2 plus I. So is, so question is 2 plus I. Cannot factor. As a product. Sort of two Gaussian integers. Yes?
2 plus I times 1.
Yes, great. 180. 2 plus I is 2 plus I times 1. Is there some other way? Yes, 1 is definitely Gaussian integer. So this number is 1 plus 0 times I. So usually we're just writing 1. So is it the only possible way? It's not the only possible way. Even in usual numbers, we can always write a number, say, I can take 6 and write it as 6 times 1, or say minus 6 times minus 1. No problem doing this here as well. So I can write this as minus 2 minus I times minus 1. there some other ways. So maybe something else. There are some other ways. The question is, what are the ways? Okay, yes. So another way. And of course, we can multiply both things by -1 and get 1 minus 2i times I. So we found four different ways of writing a number as a product of two Gaussian integers. In fact, these ways are quite general. If you take basically any Gaussian integer, if you take a plus ib, you can always write it in four ways as a product of two Gaussian integers. It's 1 times a plus ib, it's minus 1 times minus a minus ib, it's I times b minus ia, and it's minus I plus minus b plus IA. So it's quite general. We can always take a Gaussian integer and write it as a product of two Gaussian integers in four distinct ways. And kind of in usual integers, we can always write any number n as 1 times n plus minus 1 times minus n. So here we have four such ways, quite general. But what about other ways? What about taking this number and writing it as a product of two numbers in some other way? Okay, so the claim is that actually exhausted all the possibilities. The question is how to prove that there are no other ways. Suppose that 2 plus I is different number. I want to understand what are all the possibilities for Z and for W. So what can I do with this equation?
Take normal on both sides.
Okay, yes, it's so the best idea here, of course not the only one, probably the most natural one, I mean if you just think about this problem for the first time, is writing Z as x plus iy, W as x prime plus y prime, open the brackets and try to compare coefficients. It works, it's somewhat long. What you suggested is really a short and very nice way. Take norms of both sides. Norm of 2 plus I is norm of Z times norm of W. Because norm of the product is product of the norms. What is norm of 2 plus I? Yes, 2 plus I times 2 minus I, or in other words, it's 2 squared plus 1 squared. So it is 5. So here I've written 5 So I've written 5 as the product of two integers. The norm is an integer. It's a positive integer always. So 5 is a product of two integers, but 5 is the usual prime number. If it is a product of two integers, it means that one of them is equal to 1, the other one is equal to 5. So hence, either norm of Z is equal to 1 normal W is equal to 5, or vice versa. So let's try to see what can we say about Z. If normal Z is equal to 1, if normal Z is equal to 1, what does it mean? Well, let me take Z, which is x plus y. Normal Z means x squared plus y squared is equal to 1. But x and y are integers, so there aren't that many possibilities. Basically, one of them must be equal to 1, and the other one must be equal to 0. So, what are the possibilities? Well, there's 4 possibilities. X equal to 1, y equal to 0, y equal to 1, x equal to 0, x equal to minus 1, y equal to 0, and x equal to 0, y equal to minus 1. So Z must be one of these 4 numbers. And then W, the corresponding W is, well, either Z or minus I times Z, or minus Z, or I times Z. So if you take any pair here, they correspond to each other here. So if Z is equal to minus I, then W is I times Z. If you multiply minus I by I times Z, you get Z. So in this case, it's 2 plus I minus, so 1 minus 2I minus 2 minus I, and minus 1 plus 2I. So indeed we found that there are factorizations, in fact there are 8 of them. The 4 that we've written down, and another 4 is reverse order. Okay, yes, we kind of missed that on the first attempt. Yes, there are kind of 8 factorizations. Up to ordering, there are 4 distinct factorizations. And well, we always have these 4 factorizations for any integer. So probably it's a good idea to say that 2 plus I is a prime number. It has as small number of factorizations as possible. We can always factor out these 4 numbers, 1I minus 1 minus I. You can always divide by these numbers and get another Gaussian integer. But otherwise, it has no other factors. So here, write down some definitions. So definition. The numbers 1 minus 1 I minus I are called Gaussian units. And what's special about them is the following. So claim and obvious claim is going to be written down. Gaussian units are the only Gaussian integers of norm 1. So they're the only Gaussian integers whose norm is equal to 1. We already checked this. Now they will kind of defining property of what is special about these numbers. Z is equal to the Gaussian integer, which is required its inverse, 1 over it, to be a Gaussian integer. Dividing this thing is the same as saying that it's a unit. We can only leave Z Z is a Gaussian unit. So the only integer with the proper Gaussian integer with the property, the only Gaussian integers with the property that one over this number is another Gaussian integer. So here are they. 1 minus 1 I minus. No other solutions. Like in usual numbers, if you know that x is integer and 1 over x is integer, you know that x is 1 or minus 1. No other options. Kind of the same thing with Gaussian numbers. Okay, let's repeat this process but with more interesting number. Let's factor another number. So factor b minus 4I z is w or z w non-units. So sometimes it is possible to write a Gaussian integer as a product of two other Gaussian integers, such that none of them is a unit. I mean, some non-trivial factorization. I mean, of course, we have the usual four factorizations with the units, but it's interesting whether there are some other things. Well, let's see. I want this thing to be a product of z and w. Let's apply the same trick. Let's compute the norm of both sides. Norm of b minus 4I is 3 squared plus 4 squared is 25. I want it to be norm of z times norm of w. If z and w are not units, I know that their norm is not equal to 1, because all the integers with norm 1 are units by definition, well, not by definition. Here's the property. So, what are the options to factor 25 is the product of two integers. None of them is equal to 1. Well, only one option. Norm of z is equal to 5. Norm of w is equal to 5. Also, now we should find some Gaussian integers with norm 5. Does anyone know a Gaussian integer of norm 1? Or of norm 5? Okay, so what are the possibilities for z? Basically like this. It's 2 plus I. Of course I can take plus or minus 2, plus or minus I. And, well, there are some other options. Sorry? 1 plus 2I. 1 plus 2I. And once again, plus minus plus minus. So there are 8 solutions, and basically no other solutions. If you want sum of two squares to be equal to 5, well, one of the numbers should be equal to 1, the other number should be equal to 2. No other options. Well, we have 8 options. Basically, it's not really 8 options. Up to multiplication by units, which you can always do. You can always multiply and divide by units. There are only 2 options. 2 plus I and 1 plus 2I. So basically, you can just try both of them. Take this number, divide by one of them, divide by the other. Let's start with the wrong one. Hopefully. So try z which is equal to which one is the wrong one? 1 plus 2I. So if you take 3 minus 4I divided by 1 plus 2I, you'll get what? We should multiply and divide both things by the conjugate expression. So 1 squared plus 2 squared into the denominator. denominator. In the numerator we have 3 minus 4i times 1 minus 2i. And we get 3 plus 8, sorry, minus 8, so it's minus 5, plus minus 4, minus 6, so we go the right one. Okay, so we probably go the right one. Minus 6 minus 4 is it's minus 10i divided by 5 is minus 1 minus 2i. Okay, so we are lucky and we got the solution right away. So 3 minus 4i is this thing times 1 plus 2i. So actually, well, there isn't only one way to write it down as a product of two Gaussian integers. If you try the other way, 3 minus 4i is divided by, say, 2 plus I. You'll also get an answer. So 3 minus 4i is 2 minus I. We get 6 plus, no, wait. 6 minus 4. No, we are not going to get the solution. Okay, so we did get that. So minus 3 minus 8, so it's minus 11i. Okay, so if indeed we started with the other solution, with the other option, for that you will get a non-answer. You will get 2t minus 11 over 5i. It's definitely not a Gaussian integer. So basically we have only four solutions for our problem of writing 3 minus 4i as a product, or up to units and up to maybe change of order, basically just one solution. So let me write it down. Hence, up to the ordering, up to the ordering, and the multiplication by units. We have only one solution. Minus 4i is 1 plus 2i times minus 1 minus 2i. Well, I said up to reordering, multiplication by units and so on. Of course, I can multiply, say, this by I, and then I have to multiply this by minus I, then I get another solution. So we'll have several solutions, but up to multiplication by units and up to reordering, well, of course you can change the order of the brackets, there are only these four solutions. Well, only basically this one solution. So like in integers, we started with a number and we could factor it to prime numbers. Here, well, we already we checked maybe not for this exact number, but we checked for 2 plus I, if it was a prime number, it was not a product of anything but the unit times itself. So the 1 times itself up to units. So more generally, we can always start with a number, Gaussian integer, and do the following process. try to factor it as a product of two numbers. If you are successful, well, if you are not successful, if it's not a product of two numbers in any way other than, well, a unit times more or less the number itself times 1 over this unit, we'll stop here. If it can be factored as a product of two things, we'll take each one of these things and factor it to the product of things which, well, try to factor each one of these factors. So if more generally we can factor every Gaussian integer into the product Z1 times Z1 times Zk, where each Zj can be written some factor is product of two non-units. So we can always take a number and keep factoring it. If this factorable, we'll factor it and then factor each one of its factors. If it's not factorable, we'll just take this number and write it as itself. So question, why would this algorithm stop? Why do we always, well, we start factoring. One possibility that could happen is like this. You start with the Gaussian integer, you factor it as a product of two non-units. Well, each the I is a product of non-units. And then every non-unit Gaussian integer. Non-zero. So once again, we start with the Gaussian integer and we perform the following algorithm. You try to factor it as a product of two integers. If it is not factorable, stop here. If it is factorable, if it is z times w, then apply this algorithm to z and to w. Well, you'll get the product of reducible factors for z and for w, combine it. So the question is, why will we ever stop? Why is it not possible that you take a Gaussian integer, you factor it as a product of z and w, you take z, it factors as a product of z1 and z2, you take z1, it is still factorable as a product of two things, you take the first one of those, it is still factorable, and it goes to infinity. You continue this process and it never stops. Why is it not possible?
There's more on this.
Yes, norm decreases. So this stops. This stops. So the algorithm stops because z is a product of z1 and z2, and z1 and z2 are not units. Then norm of z1 is strictly smaller than norm of z, because norm of z1 times norm of z2 is a norm of z. So every time you factor a Gaussian integer into the product of non-units, the norm of the factor becomes smaller. So you can't continue to infinity. At some point you will get to numbers whose norm is very small, eventually 1, and a number whose norm is 1 is already a unit. Okay, so we have prime factorization in Gaussian integers. Next time we will apply it to some useful problems.